is a software engineer with 4 years of experience in Scala and functional programming languages. He is also interested in type-driven development, is always passionate about trying new technologies. Functional programming will save the world. That's what he thinks about current situation in the industry. Yurii, we welcome you.
Okay, hi everybody. Thanks for joining. Thanks ScalaUA for the opportunity. Let's get started. I will share my screen first of all. Give me a second. Okay. Yeah, so let's get started. The topic of the presentation may sound a little bit overwhelming, but what I want to start from is actually very simple. Give me 1 second. Yes, it's actually very simple. Let's look at this basic user class definition and think a little about simple problem of serialization. Whatever serialization, JSON, CSV, or XML, it doesn't really matter. But let's pick CSV because it's the simplest one and it's the easiest to think about. So let's just think about of how we could do this. Well, we could do it somehow like this, as simple as calling toString on all of the fields and basically separating it by comma. But that does not feel all right. It's not the best solution, I would say, because usually we have a big and complex domain model, and most of which we would like to be serialized automatically. And we can see that it quickly becomes a lot of boilerplate. So common approaches to such problems are using either reflection, writing serialization explicitly, or using macro. Of course, you could do macros for that. And in fact, most of the things we will be talking today use macro under the hood one way or another. But agree with me, using macro every time you face such problems does not make a lot of sense. It's really introduces a whole new level of complexity. And as for reflection, it's obviously not safe. Instead, it would be great if we could have a layer of API we can rely on. So we don't want to write serialization explicitly. We want to be boilerplate free. We don't want to use reflection. We want to be type safe. And we want to do things easy and customizable, manipulating with some clear abstraction and API. So that would be the main problem we would like to address today. Basically, being able to define such generic function, which can work literally with any types without writing much boilerplate. I bet many of you have been scared when seeing Shapeless for the first time. And this slide is somewhat corresponds to what I felt when I started with Shapeless. I was able to do all kinds of things with tuples, like merging them together, subtracting, adding new fields. But I felt that I missed the whole point. I felt that I didn't understand it. And when I looked into Shapeless code base, that made me want to commit a suicide, like this poor guy. But then I realized there is nothing super special there. It's not a magic, it's just a plain Scala code. But there are patterning techniques, which if you are not aware of, can make you feel very confused. And at the same time, I was very impressed by the beauty and elegance of this library. So if you feel confusion, then leave it. We will try to demystify today some of the essential techniques used in this library. And this is not going to be an expert guide. I will just share with you a way to approach to understand the library. First of all, we will go through some basic definitions, and we'll try to look at the ADT types from somewhat different, higher perspective. Then we will quickly go through type class pattern and how we can encode it in Scala. And then we will try to do some live coding covering some of the techniques which are used in Shapeless, like auxiliary pattern and lazy, and we will leverage those for generic derivation examples. And we'll take a look at some of the areas of application of these patterns. I hope I will bring to you some useful knowledge. And one important thing is that to understand what I'm talking about, you should have at least a basic understanding of implicits in Scala. Without that knowledge, this talk probably will not make a lot of sense to you. So, in order to get there, to that knowledge, let's start from the very simple thing. How do we model our domain in Scala? What are the basic instruments we usually use to represent objects from real life? Yeah, that's easy. We usually use case classes to represent objects itself and their attributes, and we use sealed traits to represent kind of variants when certain classes or objects can have different forms, be polymorphic in other words. Case classes are really nice and declarative. They are concise. There is no boilerplate like with Java beans. But what are the main problems with case classes? Because there are some. First of all, they are very explicit. The name is bounded to representation. And what I mean by that, I mean that the data representation, those field declarations inside case class, are bounded to the data label, to case class name. And we are not always interested in that. Second one is that it's hard to compose them. For instance, when you need the same case class, but with one additional field, it's really hard to do this. And it quickly becomes a lot of boilerplate. The problem with sealed traits is that it has a scope of one source file. It's not that easy to create custom sealed groups on the fly or extend existing ones. So what are the other options, more generic? Going a little bit further, we could use tuples for certain things. At this point, we are abstracted over types of the fields. Those can be encoded now into the type parameters. And as for sealed trait, we can switch to either type. Whatever implementation you want, standard library either, or cats, or ScalaZ. Now we can write generic functions parameterized by types of the values contained in the tuple. We are okay with that, but we are not okay with the size of the data. We want to abstract over the size or arity of the case class tuple. So we want to abstract over arity and kind of move this, move that red highlighted n into type parameter. And here comes heterogeneous list and coproduct as the most generic form we can get here. Yeah, just a little bit later we will see what we can do with them. And just to summarize all those things are called ADTs, which stands for algebraic data type. And case class basically, and the reason why they are called is algebraic is because case class basically represents algebraic product or Cartesian product. Or in other words, it's kind of type conjunction, logical and on types. While sealed trait represents type disjunction, or logical or on types. Using this terminology, we can think about user class as its ID and name and active and role. And we can think about role as admin or client. So I think that should be pretty straightforward. The essential thing to remember here is that HList is generic representation for case class, and coproduct is generalized sealed trait, or either which can contain arbitrary number of variants. So let's take more precise look at HList. I think most of you at least once but heard about HList. If not, the H list is the kind of a list which can hold elements of different types, and it holds type information about all of them. So the instance of H list basically looks like this. And you can do actually all kinds of things as this standard list, like getting a head or tail. And you can do more. For instance, you can select a value by its type. Interesting functionality, but you can do this. And if you look at type, which is commented here, you can see it is just a nested structure, and at every level of this structure, we preserve type information about the value it contains. The form it is written here is using infix syntax, which makes them really nice to work with in Scala. The same syntax we use to work with standard library list. If we look at the definition, we can see that it's very simple. We have two subtypes, one called hnil, which represents an empty case, and another called hcons. From now on, we will call this double colon as hcons. And this looks very similar to a regular list definition, as you can see. The only difference is that the tail of the hlist, or hcons, holds its own type information. So it has additional type parameter here. So it is based on the idea of type recursion, kind of. Pretty much the same thing goes with coproduct, but unlike hlist cons, it has two variants, either holding a value or a tail, which is also either a value or a tail. And here is the usage of it. As you can see, unlike hlist, we can't use the same syntax to construct. So overall, the coproduct can have only one value, but still preserves type information about all values that can be contained in it. And the value of it determined by the path made by this in L in R, which constructs the instance. Unlike hnil, cnil doesn't convey any information. So this is achieved through not having any value for cnil by using seal trait. By the way, the strange hlist name is because product name was already taken in Scala standard library. So the creator of the library chose hlist name. Okay, now we know how hlist looks like, but how can we go from case class to hlist representation? And one of the essential instruments in Shapeless is called generic utility, which provides us with this nice mechanism to convert between product representation and its generic representation. Here is the example usage of it. You can pay attention to resulting type, and you can see that we get a type which has a type member, which has a type of hlist, holding the type information about each field of the user class. Looks pretty straightforward. This is the definition of generic type class. And there are type of the generic representation, type member, and two methods to convert to and from generic representation. So this is how we can use it. Here, basically having an instance of user, we can convert it to hlist and convert back into a case class form. I want to pay your attention again to this type wrapper. The instance of this trait holds a generic this generic type, which is either hlist or coproduct, depending on the type of the value we supply with type A. Basically, if it's a case class, then this type wrapper equals to hlist, and the same with seal trait and coproduct. Okay, so let's leave hlist stuff on the side just for a moment and talk a little bit about the type class pattern. I won't quickly go through this in case if somebody is not familiar with this pattern, so we are all on the same page. Yeah, and as you can see, this guy is a little bit overwhelmed here, but that's understandable because although set-time core functionalities in Scala standard library are built across type class pattern, there are only a few mentions of it in the whole code base. And this is kind of strange to me because, as you can see, such things like numeric ordering can build from in fact type class pattern, but there is no mention about that in the code base. And yeah, so whenever you do sorting in Scala, you actually use type class pattern. And by the way, all of the functional primitives from the popular functional programming libraries like ScalaZ, cats are defined using type class pattern. In order to understand, let's take a look at this simplified version of ordering trait. And by the way, you can see it implement Java comparator. So for those who has more experience in Java, just think about comparator and you will understand it. The basic building blocks of type class pattern are first, definition as a parameterized trait, because if it's not parameterized, then the whole pattern doesn't make sense. So it should be parameterized by at least one type parameter, and it should have at least one method. Second, implicit instances, usually defined in a companion object. You may ask why in companion, because this is one of the scopes where compiler will look for implicits automatically without special import. And the third, the usage, usually in the form of implicit parameter or context bound. So these are the main building blocks of the type class pattern. And to distinguish it, you should start from looking up a parameterized trait. And if it's used somewhere as an implicit parameter to some function class, then it's probably a type class pattern. And instances actually can be defined anywhere, but usually they are in a companion object. Let's take a look at the usage. At this point, compiler looks into companion object scope and tries to find an instance of the ordering type class for the integer type. Yeah, so this is very functional type of polymorphism, or ad hoc polymorphism, as it's called. And there is a very nice library called Simulacrum, which introduces kind of first-class support for type classes in Scala using macro. This macro produces quite a lot of noise, but that can be considered as a full canonical type class pattern. Cats library uses it. All of the type classes in that library are defined using this macro library. So let's return to our initial problem with serialization. First of all, let's define a type class, which will define an interface for serializing. At this point, there is nothing complex here, as you can see, no implicits or anything like that. We've just captured very basic functionality into a simple interface. And let's define some helpers in companion object, one for materializing implicit instance based on type, and one implicit class instance to be more, just to be more declarative. All right, so now comes interesting part. Now you can go to the GitHub and download code, so you can follow me with this coding session. And I will switch to the text editor. So what I have here, actually, I have already what I've showed you, type class definition, and I have instances for primitive types, for simple types, for long, boolean, and string. You may notice the syntax I use here, and that's because I'm using Java 8. I'm able to define an instance of functional interface simply using syntax for defining a function in Scala. So this is equivalent to this, actually. Just simply defining an instance, an anonymous instance of this trait. So again, so what is our goal? Our goal is to get an instance of this type class, CSV serializer, for user class, which is defined here in the top. And we already seen that we can convert to and from generic representation. So if we build instances for HList, we can build instance for the initial case class easily. Yeah, so let's start. Yeah, you can see I have already this HNIL serializer instance. It simply returns an empty list because HNIL is an empty case. There is nothing to serialize. And I will try to define an instance for HProngs. Yeah, so it will look somehow like this. So I already see that I have type parameters here, so I should make it not a value, but a method, and parameterize by this type, these two types. H type is for a head, and T for a tail, which in turn should be of type HList. And yeah, so what should I write here? Actually, if I have an instances for an instances of serializer for a head type and for a tail type, I can basically serialize head and tail and then just concatenate it. So what I can do here, I can tell a compiler to provide me with implicit instances for a head serializer, like this, and for a tail serializer. And having this, my definition will look like something like that. Then just concatenate with tail, with serialized tail. Let's look if it compiles. I hope so. Yes, it compiles. So you may notice that the syntax, the implicit keyword in the one scope of parameters of a function can be used only once. If I use it, all of those parameters are considered as implicit parameters. So what's next? What's next? We already have instances for HList, and we can use them to build an instance for our user case class, for arbitrary case class. And I will name it generic serializer, which should take, which should provide an instance of serializer of arbitrary type A. And what I need here is an instance of generic for type A to convert to and from generic representation of type A. And I need a serializer for generic representation. And as you remember, there was a wrapper type inside the generic instance. So I can use it like having something like this. This is like intuitive solution, but we will see if it compiles. Yes, it doesn't, and compiler says there is a legal dependent method type. Parameter may only be referenced in a subsequent parameter section. So what happens here actually? What does it mean? The meaning is that we cannot refer to a type member of another type parameter in the same scope. We cannot refer to a type which contained in the generic, because generic is in the same scope as wrapper serializer here. So what we can do, we can move the this type parameter into actually here. I will name it wrapper 0, and do one tweak, which will look like this. And here I will use this new type, wrapper 0. Let's see if it compiles. Yes, it compiles. Actually, it's valid Scala. We can write like this. And I want to return to the presentation. And the reason of existence of this pattern, because that was the pattern actually, well, that was the reason of the auxiliary pattern, is rather simple, but you might be confused if you are not aware of this reason, and you just see these aux definitions all over the place. And having this simplified example, we can see where this aux type appears. And actually, as for generic type class from Shapeless library, we have auxiliary type defined in the Shapeless library. We can use to substitute this code with a little bit more readable version like this. So this is called auxiliary pattern actually. And let's see if it compiles. Yes, it compiles, but let's finish our implementation. What we need to do here, having an instance of type A, I will convert it to generic representation first. And then serialize it using this serializer. Yes, let's see if it compiles. Yes, it compiles, but let's test our solution. I have a user instance here, and I will try to serialize and print it to the console. Yes, as you can see, it works. But let's try to do to use it for a nested structure. I have a definition for account case class here, and it is nested structure which has one case class and type and field member of type user. Let's see if it compiles. It doesn't, and compiler says us that there is divergent implicit expansion for type CSV serializer, as you can see here. Cryptic message, what it means. Let's return to our presentation. Yes, to better understand what happens here, let's go through implicit expansions one by one. While searching for an instance for serializer for account type, compiler will expand it to a nested H-list structure first, and then we'll go through each of the nested HCons elements, as you can see, on steps 2, 3, 4, until it finds a user type. At this point, it will expand it into a generic H-list representation, and it will find out that the same type constructor, I mean HCons, is used again, but complexity of type parameters is higher. So HCons on the step 5 is more complex than on the step 2. And the compiler thinks that we are cheating and the recursion will never end. That's what this error means, actually. To overcome this exact problem, Shapeless has a nice instrument called lazy. And it uses macro under the hood. And what it does, it suppresses implicit divergence at compile time. And it kind of defers evaluation of the implicit parameter to runtime. Yes, so let's return to our code. And let's use it. Here and here, so yes, and additionally, I need to unwrap the value contained in a lazy. Let's see if it compiles. Yes, it compiles. And that means we are able to serialize the count too. So yes, so that is actually a whole solution to our initial problem. And I want to pay your attention that I don't need any more serialization logic to write here. Besides maybe only more instances for simple types, like long boolean instance for double probably. And I can serialize literally any case class. It is concise, type safe, and clean. So this is what derivation means essentially. Using type classes, we were able to derive instances for composite type while having instances for separate components of that type. And what Shapeless does is basically providing an instrument to work with ADTs in a generic way. It provides us a possibility to abstract over arity on number of arguments and write functions like to CSV in a more generic fashion. There are a couple of other instruments in the library, but the main one is to abstract over arity, is what it's all about. At this point, we can give some definition to what generic programming is. And speaking simply, whenever you use generics, you do generic programming. And that means you do a kind of programming when you write algorithms in terms of not yet defined types. In such ways, we are generalizing over common properties of types. However, in some cases, it's easier to abstract over a particular property, like type of the field of the user class. In others, it's harder, like arity. As we have already seen, sometimes it's hard to deal with errors in our code. The compiler errors can be obscure and not descriptive. And if you have a big nested structure, it might be a problem. Usually, you should debug through that nested structure one by one and look at every implicit definition precisely. And at least it fails at compile time and will not produce runtime errors. In any case, you should be aware of these tools, like implicitly and there. You can use Rife for debugging the resulting AST. It will show you inferred types too. And of course, you should be aware of k-bindings in your IDE for working with implicits. And once you know these shortcuts, you should feel comfortable working with type classes. Otherwise, it makes you feel something like that. And a few words about known issues. Because, of course, everybody heard about compilation times issues with Shapeless. But usually it heavily depends on the use case and situation. There are still bugs in the compiler, which can cause a huge overhead and very long compilation. One of those bugs is fixed in type level fork of Scala. Its name is inductive implicits. And as for runtime overhead, there is very little, if any. A few additional calls in the stack trace, almost nothing from my point of view. And you actually see the definition of hlist, which looks very similar to regular list. Yes. So all this magic happens at the compile time. In the runtime, very little is left, just raw objects. To summarize this talk, Shapeless is a very powerful instrument, and you should use it carefully. You should remember always to choose a minimal abstraction needed. If for certain cases, case class is sufficient, you should stick with case class. You shouldn't be using HList everywhere. I hope I gave you a basic understanding of the techniques used in this library. And once you master them, you shouldn't be scared of Shapeless anymore. Everything should be clear, I hope so. And once you master those techniques, you will start seeing use cases all over the place. Usually the common use cases appear on the so-called edges of your application, where you interact with the real world. Database, I/O, and serialization is one of the examples. There are a whole bunch of other stuff in Shapeless. Polymorphic function values, poly, which can be used as inputs to a map of a HList, for instance. There is generic ops package, which provides all kinds of operations of a HList. There is type class, it's not a joke. There is piano numbers. You can use them, for instance, for manipulating the size of HList at compile time, or get the type of the nth element of HList at compile time. Very interesting thing. And there are boilerplate-free lenses and other utils, actually a lot of stuff. But the main one, again, is actually ability to convert actually from regular product representation to a generic representation. You may wonder, what are those astronauts pictures scattered across the entire presentation? Well, that's because of that awesome small book by Dave Garnell. And actually, this whole presentation was totally inspired by it. You can find it on Shapeless GitHub, or you can order it. So don't be scared about Shapeless. Later types do work for you, so you can just get back and chill out like this, or maybe like this, wherever you prefer. Yeah, small pieces of code from the presentation you can find on my GitHub page. Thanks for watching. Any questions?
Thank you very much, Yurii. Let's wait a couple of seconds for questions, if it is right. No questions by now. So I think if some questions appear, so we can find it on our comments to the video on YouTube channel. Yurii, thank you so much for your presentation. It was very, very interesting. So thank you. See you.
See you guys. Thanks.